There's already enough people that drop out.
Well, what happens? Something happens like everything turned off, and then there's like digital example. I couldn't get like things to play.
You said you couldn't get anything to play?
No, I can just break it. Nothing works. I can't even think that killer.
Something's gonna make it work. Poor little thing. There you go, Jeff. Turn it on. Alright.
It's like a black and white Rubik's Cube.
Yes, Rick?
That's the name, don't see, I got physics this
So if you weren't here yesterday, here's what we did. I'm not going to do it again. So we found critical numbers, we found the max and the min. Second derivative, we found the critical numbers for the second derivative. And those are where what might happen?
It's where the point of
Yeah, inflection point might happen. Cool. And on this one, it just happens to turn out that they both turned out to be inflection points. Doesn't have to be that way, right? They're both inflection points because what happens? The concavity changes on either side. I like it. Cool. Okay. So to finish this out, again, we all have calculators, thankfully, so we have to plug -1 over rad 2 into this function to see where the heck it is. -1 over rad 2 comma something. Somebody help me out there. Maybe I'll help myself out.
With numbers, right? I mean, I changed it to -0.71.
downgraded? Actually, that's 18 plus, so that's 2,000.
So this one I get. Oh, for this one I get 1.24. And for this one is -1.4. Cool. Alright. That was exciting. Watching me punch buttons on my calculator.
Question? Does it matter if we leave it as -1 over root 2 or like that?
Yeah, for the purposes of graphing. Well, I'm gonna. What is -1 over rad 2? It's -0.71 roughly. Yeah, -0.71, and this is positive 0.71. I like it. Cool. Like it, which is still even too much for by hand, but oh. Okay. So we have investigation of the first derivative, and we have to understand what it means, right? So you know first derivative means slope, so that's why it leads to the idea of maxes and mins. That's why I can find them using it. Second derivative tells me the curvature of the graph, right? So it's just one extra dimension that we didn't have in pre-calculus when we were graphing functions. I didn't, if it was going up, I didn't know if it was going up like that or going up like that. And your teacher shouldn't have cared because you didn't know, right? So now we do. So find the intercepts. What are the intercepts? So the function was 5x cubed minus 3x to the fifth. What's the x-intercepts?
0 square root of 5.
Yeah, because you can take an x cubed out. Right, that'd be 5 minus 3x squared. So you get 0. And yeah, square root, plus or minus square root of 5/3. Holy shit. And what's the square root of 5/3? I don't know. 1.31.
Yeah.
You're doing math.
Are you?
Mathematics.
What's that?
You're doing that in your head?
Dude, he's done it so many times.
Yeah, square root of 5/3, that's just a known thing. 1.29, alright. Not too bad, close. But come on, 5/3 is close to 2. Square root of 2 is 1.414. A little bit less than that, and that's a good guess.
Come on
That
now.
makes people being semi-serious. I mean, I want you to understand it's not something. But see, it's nice that we have calculators and we're able to do a lot more than ever before. But we're losing more and more touch with numbers themselves, and that's huge. You guys are like, shut up, man. But it's just true, and I'm obviously not coming down on you because everybody else is like, I don't know. But I'm just letting you know how I can approximate things, and it makes it feel like, oh wow, Jeff did all that in his head. No, I'm like, I know how I can get close. I don't know what the real answer is. I can get close enough to make people go, oh wow, you're amazing. No, I'm not. So this is plus or minus 1.29. Okay, so then we can graph this a little bit better. So those are the x-intercepts. My y-intercept, of course, is already known as 0, 0. Right, is that cool? Yep. Let's see, blah, blah, blah. So what do we got here? We got the mins we can put on there. Let's go and put the x-intercepts on there. So, let's see. Negative 1.29 is about right there. Positive 1.29 is about right there. And 0. Thank you, Steve.
Yes, sir.
And then we got the min is negative 1, negative 2. So negative 1, negative 2 is the min. And the max is 1, 2. So we put min there. And we'll put max there. Notice a little tiny detail. I write min underneath it. And then my graph won't go through the word min. Right? Little tiny thing, but still. What else we got? Concavity, inflection points. Negative 0.7 roughly, so negative, everything's happening. Let's do this. Right now I'm realizing something. What am I realizing? I didn't even stop to think about my scale, to be honest. Yeah, I should blow this scale up, right? I should maybe make it at least 0.51. In fact, let's see.
Draw my hand.
Yeah, let's do this. You ready? So I'm gonna. Do I have any extra copies? Shit. Can I even do what I want to do? No, too bad for you, Jay. But your scale, if you start to graph it and you notice something like that, you're like, whoa, this is all really compact. Then just redo it and make your scale give yourself a little more room. Oh, thank you. Okay,
Let me help you out there, man.
I appreciate that. So let's see. What am I talking about? Let's make it, let's do this. Let's make it 0.25. Let's be crazy. Oh, wow. We're off the hook here. Oh, my gosh. I like the way I said that.
Is that how you youngsters say it?
All right. And then the scale here, what's my largest outputs? Well, my minimum, my local min is negative 2. My local max is 2. So I can kind of blow up the scale here, too. Not as much. Let's do 0.5, 1, 1.5, 2. 2.5. What's most important there is you understand my motivation for... No, Jeff, you can do it. There you go. My motivation for what I'm doing. Alright, so let's try this again. So there's 0, 0. What else we got here? We got...
1.29 and negative 1.29.
Yeah, 1.29. So there's 1.25. Oh well, so that's very close to that. And then negative 1.29. I like it. Cool. And those are my intercepts, right? Yes. Cool. And let's see. Blah 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 blah. My max and my min. My min is negative 1, negative 2. My max is 1, 2. And my inflection point's negative 0.7. So just below that. Negative 0.7, negative 1.24. It's a little bit below 4 there. And then positive 0.7, positive 1.24. I'm not labeling these poor little dudes as I do this, and I should be. Should be right there. So this was my max. This was my min. This is an inflection point. This is an inflection point. Right? Now, of course, to the untrained eye, it looks like it's straight line.
Well, you forgot the other point.
Oh, which one?
1.29. The intercept?
Yes.
The intercept?
Are you saying label? You're just talking about you didn't label it.
Oh, yeah. Well, if it's on the x-axis, if it's not labeled, I know it's just an intercept. Is that cool? You guys with me? All right. Okay, cool. And a little something. Let me see if you guys get this. If an x-intercept is not a max or a min, what's my function going to do there? It's going to go through. It kind of makes sense. And the only way an x-intercept could be, the only way I'm going to turn from it is it's going to be a max or it's going to be a min. And if you look back at the multiplicities of my x-intercepts, they're odd. That one's odd, and the two of these would break that up into x to the first. That would be also odd. So it is going through all of my x-intercepts. The only way it would turn is if they were maxes or mins, and they weren't. All right, do you have to actually know everything I just said? No. But it would help. Okay. And what's the end behavior for this? Let's just bring that into play. What's the end behavior for that function?
It's gonna keep going.
That's funny. I like it. Let's see. Keep going. Be a lot more specific.
Go down.
Oh, on the left side, it's gonna go up. It's gonna be. So it's just negative on the left side. That's what's happening.
Yeah. So it's negative cubish, right? So I call cubish. I call this cubish. That would be if it was positive, but it's negative something to the fifth power, right? So it's going to be negative cubish. So it's going to go like this. So that's my end behavior.
That's what.
Gotcha. That's awesome. I love it. Just wait till the teacher says it. Just like that. Okay. So now that's my x-intercept right there. So I know I'm going to come. So I can kind of see what's happening here already. And as I go, so my end behavior gets me started. Something like that. And then it's minimum there. So I got to turn there. And it's I don't know if you guys. I pretty much know this already, but for you guys, you should be careful. I start with concavity up, right? All right, so you got to keep your eye on all these things. You got to the end behavior and the original concavity get you started, and then you actually never have to look anywhere except your labeling. So I know it starts off from up here, and I know it's concave up to start with. When does it become concave down?
At the inflection point.
Right there. So then, what I was telling you guys was, now this is going to be a little weird. What's going to happen through here?
A little bit off the.
Whoa, sorry. My only inflection points, there were only two of them. So now it's got to be concave down all the way up through there, right? Yeah. So it's going to be a little bit strange. Let's see. So it's going to change the concave up here, which kind of makes sense, right? Well, that's your max, Jeff. Get out of it. Get out of it.
It's got to be an inflection point right there, right?
Yeah. So it's got to now it's got to become concave down. Go through there. And then it's going to become concave up. It's a very freaky graph. Concave.
Yeah,
It's really weird.
Zero's an inflection point. It's gotta be.
There should be a curvature somewhere.
Oh, here, yeah. Why did we leave poor little zero out? Oh, that's right, because yesterday we didn't. All right, let me catch up myself. Exactly. Zero's got to be an inflection point, the way that was coming out. We left off right before we figured out these points, right? And I just forgot that zero was also here. So, of course, if you do this, you probably shouldn't leave a full day between parts of a problem, because then this kind of thing could happen. So at zero is another inflection point. We knew that from yesterday, it just didn't get collected. So at zero, what's the function, of course? Zero. Okay, so we knew that already. All right, so one more try. All right, can I salvage that? No, there's too much shit in the way. Too bad. So it makes, that would be really hard to do. So it's concave up, and then it's concave down, and then it's concave up right there. That's another IP, that's another inflection point. I like it. So that makes it go through smoother. Otherwise, it was almost like a straight line through there. That's a little weird. All right, so concave down, and then that's an inflection point, so now it becomes concave up. That's an inflection point, so now it becomes concave down, which makes sense, because at the max, it should look like a parabola almost. And then it's down through. Craziness. So ignore that. The benefits of doing this in pencil. It's crazy. Alright, and you can always double check. I would highly recommend that you try to not graph it in your calculator or Desmos or whatever until you've actually got something down there. Otherwise, you're being biased from the beginning. You kind of know what you know. I want you to really trust your work. And another thing, if you do the work, let me see if I can get you guys to understand this. The graph you make must match what you found in your work. You understand? So if you graph it and you're like, oh, it's supposed to be concave down, but I don't see why, draw your graph wrong. Right? Don't copy what's in the calculator. Draw it based on what you find. You'll keep more points that way. I will take more points off if your graph doesn't match your work, because the big thing I need to see is, do you know how the actual calculations you made, how does it relate to the visual of the graph? So if you're just copying your graph from the calculator, you're totally missing it. You're going to lose all those points. Does that make sense? So I'd actually much rather prefer a wrong graph, because you got something mixed up in your work. You guys with me? A little bit. Okay, cool. Okay. Woo! Any questions on homework? I just want to get that out of the way real quick. Any questions on homework stuff? Okay, I'll take that as a collective no. So, some of you guys have already used this idea, so you've been desperately waiting for this to happen. We are finally going to discuss something called L'Hôpital's rule, which is really strange. It's not the rules of the hospital. You'll see a lot of places claim that there's no S there, but L'Hôpital himself put an S there, so I'm going to defer to the man himself. Alright, so it's spelled like that. If he spelled it wrong, then that's the way it's spelled now, because he's him. So L'Hôpital's rule. So this relates to finding the limits, the limit of a ratio of functions. So let me, I was trying to decide how rigorous of a proof of this I wanted to show you. And I think I just now decided to not go whole hog on this. I had two options here. Not so rigorous, a little more rigorous, right? Let's try the not so rigorous one. Let's see what you guys think. Remind me, let's say, what would the linear approximation be for this function? And let's say at a equal to x1. Remember what was the linear approximation for this? F of x1, like f of a, plus the slope times x minus a. Right? It's just m times x minus x1 plus y1 equals y. Right? Let me stop there for a second. So then what would g of x, incredibly enough, it would just be g of x1 plus g prime x1 times x minus x1. Alright. So in your notes you might want to write this a little differently, but I'm going to use what I've already written. So if the question is, what's the limit as x goes to, let's see if I can keep you guys with me, as x goes to a of f of x over g of x. Alright, so I'll let you figure out how you want to do your notes. You want to rewrite all this? It's up to you. I can say that should be approximately equal to the limit as x goes to a of this ratio. Are you guys still with me a little bit?
You can just limit law, right?
Huh?
You can just use the limit laws, right? To break that. Okay, anyways, yeah.
And so I just wanted to make sure this by itself was kind of understood. You could do this. And a is this x1, so I mean, it's actually going to become perfect at x1. This would be perfect, because where's the only place that this linear approximation is perfect? At the point where I built it around. Alright, let me stop there for a second. So all I did was replace the function with its linear estimation. All right. So what L'Hopital's rule looks at is these limits that are indeterminate. So we know these indeterminate limits. We know what they look like. Give me, what do they look like? What's one indeterminate form? 0 over 0. I like it. Because number over 0 is not indeterminate. That's infinity. I know it. I can determine the answer. So indeterminate means, oh shit, it all depends on who's getting there faster. Which is why it kind of intuitively makes sense. It should depend totally on the slope. So what if I had this? So this is true here. In general, this is true. What if I had the limit as x goes to a of f of x over g of x, and that was in the form 0 over 0? So normally back in the past, what would we do? We try to, if there were radicals in there, we would multiply by the conjugate. If there were polynomials, we would try to factor them, right? But can I always do something like that? What if it was a trig function over something? Shit. We're screwed. So we need something more powerful than that, because we can't do those things to every function. So what does this say then? What's the limit as x goes to a of f of x? Well, what is this telling me that it is? 0. And what's the limit as x goes to a g of x? 0. Okay, cool. I like it. So they're both going to 0. So the whole thing is, it's sort of like, it's exactly like back in pre-calculus when you did this, and you let it go to infinity. It all depended on who was going to infinity faster, right? So this would be infinity over infinity, but which one's going there faster would be the bottom, and that's why this would be 0. I like it. So this idea is the same idea now. I like it. Cool. Oh, let's see which way I want to go with this. Oh, all right. So when I look at this, what did we just say about... x1 is actually... this is the little piece that I can't get away from. x1 is somewhere in between x and a. So every time I move a little closer to a, x1 gets a little closer to a, possibly. So there's some point in there. But what's the limit from what we just did? If we have a function, we have this situation here. What is the limit as x goes to a of this?
0.
Yeah, this is 0. And what's the limit of this? 0. And what can I do with these? Cancel them out. So this limit equals the limit as x goes to a of f prime. And this is the one little piece. x1 is somewhere in between these two, so eventually that becomes what x is, because x is pushing it towards a, and then eventually they're going to become the same. That's the little technical piece of these proofs that I'm trying not to get too deep into. Right? So the idea that this captures is if a ratio of functions is in an indeterminate form, then the actual answer depends on the rates of how quickly they're going to those things. And we've known this actually for a while. We knew this in pre-calc. In fact, you said it like that. X over x squared plus 1, it depended on who was going there quicker. So let's do a concrete example, right? This is my attempt at a little quick proof. So here's a concrete example of this. The biggest mistake people make with this is that they apply this when it's not indeterminate. When it's not indeterminate, L'Hopital's rule is like, I don't know what's going to happen to you. You could totally change their answer. It could be totally wrong. It only keeps the answer the same if it's indeterminate. Let's do one that we can figure out easier, a different way. Just so we can see if this, that we can verify for ourselves that this works. Something like this here. Who could tell me real quick, just by factoring, what would the answer be?
2.
Yeah. You factor the x plus 1, x minus 1 goes away. X plus 1, when you plug a 1 in, you get 2. So the answer should be 2, no matter what method I use, as long as the method is valid. So, but what form is it in right now, before I factor? What form is it in? Yeah, because what do you get?
0.
0 over 0, I like it. So it's in that form. No, Stay away from saying this equals 0 over 0. It's in this form. To say that it equals 0 over 0 is like saying it equals blank. You know, it equals shit I don't know. It doesn't make any sense. Just say it's in that form. I got to do something to it to make it make sense. So, can we apply L'Hopital's rule?
Yeah.
Yes, thank God. That's the whole purpose of the day, Jeff. So normally I say, I do it like this. I'm applying L'Hopital's rule right now. That helps me grade your work, and it helps you go back and say, how the hell did I do that shit? Put that for yourself so you remember what the hell you did. So what is the derivative of the top? 2x. And what's the derivative of the bottom? 1. Is that still indeterminate?
No.
Obviously not, because the bottom's 1. It's not infinity over infinity. It's not 0 over 0. Right? And when you plug a 1 in, sure enough, you get 2. Holy shit. If you took one more derivative, you would get what? 2 over 0. And then you think it's infinity, and that's L'Hopital going, hey, dude, you're out of my hand. I don't know. I can't take the blame for that shit. See, people do that, and then they say, L'Hopital's rule doesn't work. And I'm like, it totally always does. You were in a situation you couldn't use it.
You wouldn't need to put the over 1, would you?
Well, I just did it just to show what the, it's a derivative over the derivative. Now, a real quick thing. I am not taking the derivative of this. Please, dear God, anybody who still doesn't quite understand quotient rule, don't take this as validation that you can just take derivatives of each. That is not what's going on. The rule says that the limit of f over g is the same as the limit of f prime over g prime. I'm not supposed to do a quotient rule here. I'm taking the derivative of each separately. I like it. Alright, so what about here? Remember this thing here? I don't know until you write it, Jeff. Remember this evilness? There was not shit we could do with it. We just had to graph it, and we just had to go and say, sure, it looks like it's 1. Why not? But now, what form is it in? Indeterminate. So I can apply L'Hopital's rule. This is in the form 0 over 0. So if I apply L'Hopital's rule, what do I get? Cosine over 1.
So it's 1.
Yeah, and when you plug a 0 in, you get 1. Holy shit. So you can look back, if you look back in chapter 2 and say, these were really hard. Now a lot of them are stupid easy. Right? Because now I can just, and of course that's before we knew derivatives. So I couldn't show you that. Alright, so here, let me let you guys try a couple. And then we'll have to talk about other forms. Real quick, if it was infinity over infinity, like x over x squared plus 1, right? If I was going, let's say, if I'm going to 0, let's say if I'm limit as x goes to 0, let's see, Jeff. 1 over x over, what you got, Jeff? I don't know, Jeff. 1 over sine x. It's crazy. Kind of giving a silly example, but isn't that infinity over infinity?
Yes.
But can't you just reciprocate stuff and then the whole little mini proof I did applies? So infinity over infinity is equivalent to 0 over 0 if I just reciprocate everything. So everything still holds for that form. There's one more form after that we have to, well, 2 more forms after that we have to talk about. So here, you guys try this. Let's see what you got, Jeff. Let's make this actually work, Jeff. What am I trying to say? 0. There you go. I like it. And what was the other one? Oh. Yeah, let's see that. Oh yeah, that's true. Alright, so each of these is in one of the forms, indeterminate forms we've looked at so far, right? 0 over 0, infinity over infinity. This guy is 0 over 0. So you can apply L'Hopital's rule. So what do you get after you do that? Yeah, negative?
Secant squared.
Cosecant?
Over 1.
1. Good. So now it's all about evaluating cosecant squared, right? Because it's not indeterminate anymore. If it was still indeterminate, like what you get here, you just keep applying L'Hopital's rule until it ain't. Right? L'Hopital doesn't care where you started or how many you've done already. It's just like, do you currently have an indeterminate? Use me. Do you currently have an indeterminate? Use me. Right? So that's why I can keep using it over and over. Here, I just need it once. But what is cosecant squared of pi over 2?
-1.
Yeah, because it would be 1 over sine. Sine is 1, so negative, so it'll be -1 over 1, so you get -1.